Hi, welcome back. We're on to one of the final sections of the course, BCS theory. This is non-examinable. Before we get going, I would like to impart some wisdom as to how to survive physics during the lockdown. And I have two words of advice. Chocolate, good chocolate preferably, and coffee. Excellent. Okay. So, BCS theory of superconductivity. Recall from the beginning of the course, superconductivity was discovered in 1911 by Campbell-Ioannis, and the full microscopic theory of superconductivity wasn't developed until the late 1950s, 1957, by Bardeen, Cooper, and Schrieffer. And maybe I'll even write that out because those are important names. BCS, Bardeen, Cooper, and Schrieffer. So Bardeen was the senior professor, Cooper was the postdoc, and Schrieffer was the graduate student. This is undoubtedly one of the great intellectual achievements of the last century. Bardeen had already become quite famous because of the invention of the transistor at Bell Laboratories in 1947. He was actually pushed out of Bell Laboratories by his manager and also sometimes collaborator, William Shockley, who more or less prevented him from ever working on transistor physics at Bell Labs ever again. So he moved from Bell Labs to Urbana, and in 1951 began his work trying to understand superconductivity. Now we already sort of know what the answer is going to kind of look like. We know that superconductivity is going to have something to do with pairing of electrons into bosons. You take two fermions and you stick them together to form a pair. That pair will be a boson. And this idea had been floated before the BCS theory of superconductivity, but it wasn't very popular. As a matter of fact, people didn't like it at all. Some people were extremely opposed to the idea of electron pairing, including the great Lev Landau. And there's good reason why people oppose this idea of superconductivity due to bosonic pairs of electrons. First of all, electrons repel, quoting Lev Landau. You can't repeal Coulomb's law. And secondly, even if you could get them to pair, so pairing two electrons equal one boson, that this is actually, to make it really a boson, to be really a boson, we would need to have the binding radius of the boson, so the radius of the boson, what should we call it? Binding radius, that's going to be the binding radius, we would need that to be less than the distance between bosons, less than distance between. Otherwise, if the binding of the two particles into a boson is greater than the distance between the bosons, then it's not like you have bosons; it's like you have individual electrons. So the problem is, to get the binding radius this small, you would need a binding energy to be on the order of a Rydberg, on the order of a Fermi energy. Binding energy would have to be on the order at least of the Fermi energy, which is a huge number, 10,000 Kelvin or something like that. And certainly, even if you can generate some sort of attraction mechanism between electrons, something to try to glue the electrons together, it's going to be very hard to imagine coming up with an attraction mechanism that will come up with glue that's strong. So for this reason, no one really liked the idea of binding electrons together into bosons. So in our study here, let me move myself out of the way. In our study, we're going to first discuss what the attraction mechanism comes from and how it forms pairs, and then we'll go to the full-blown BCS theory in the next lecture. So the attraction mechanism, well, actually, there are different kinds of superconductors. There's what we call the conventional superconductor, sometimes known as the BCS superconductor. And in conventional superconductors, the attraction mechanism, conventional mechanism is an attraction due to phonons or lattice vibrations, phonons. So this is some sort of interaction between the electrons and the positive ions left behind that vibrate to create the phonons. And this was, even in the early 1950s, a number of people had started thinking about whether phonons could somehow be important for superconductivity, including Feynman and Froelich and a number of other great scientists. In fact, in the 1950s, a lot of the greatest minds in the world, a lot of the greatest physics minds in the world, were thinking about the problem of superconductivity. Landau, Feynman. It was sort of a period in history when people had sort of lost faith in high-energy physics, and they thought maybe there wasn't anything interesting left to be done in high-energy physics, so let's see if we can tackle some of these problems that have been sticking around for a long time, like superconductivity. Okay, so in the conventional so-called BCS superconductors, the mechanism that is going to bind the electrons together is going to be phonons, but there are unconventional mechanisms which can come from other sources. So there are many, although not as many, but there are many modern superconductors with unconventional pairing mechanisms. This includes the high-TC perovskite superconductors, the more recently discovered pnictide superconductors, helium-3 as a superfluid. Remember when the two helium-3 atoms can actually pair together to form a boson as well. And in the case of helium-3, there are no phonons. It's just the helium-3 atoms. There's no background lattice whatsoever. So obviously there are other mechanisms that can do the job as well. And many of these unconventional mechanisms are more controversial, and still have a lot of people researching them even in the current era. So in the case of high-TC superconductors, the perovskite superconductors, there's probably on the order of 1 million research papers, that's not an exaggeration, trying to figure out something about the mechanism of high-TC superconductivity, and still there's no agreement as to what the mechanism is, but it is believed it is not phonons. So, as I was saying, even in the early 1950s, people had a feeling that phonons were going to be important. And there was a real important clue to this, to see that the lattice vibrations, or the phonons, what is going to be, so let's see, in the case of conventional superconductors, the important clue is known as the isotope effect. Which, so remember, isotopes of atoms are different versions of the same atom where you change the number of neutrons, you keep the same number of protons, you keep the same number of electrons, you just change the number of neutrons. The chemistry of the atom stays completely the same. The electronic properties of the atom stays completely the same. The only thing that's different is the mass of the nucleus. And what was found is that the critical temperature for superconductivity depends on the mass of the nucleus, where alpha is approximately equal to 0.5. It varies a little bit depending on the on details, but there is a distinct dependence of the critical temperature on the mass of the nucleus, and the only thing that that could do that is if the actual vibration of the nucleus, the motion of the nucleus moving back and forth, is somehow involved in the mechanism. If the nucleus was completely stationary, then there would be no isotope effect whatsoever. So by adding some neutrons to the nucleus, you see a change in the critical temperature, which tells you that the vibrational frequency which depends on the mass, the vibrational frequency of the nucleus is somehow getting into the game, and that tells us that phonons are somehow important. So, so what we're going to find that that this phonon mechanism is going to be strong enough to actually induce this BCS pairing and give us superconductivity. And there's a couple of important lessons to be learned about this. The first important lesson was that Landau was actually wrong. That there were a number of cases. We already found this case of vortices. He didn't like the idea of vortices, so he was wrong about that. And he was also wrong about not being able to repeal Coulomb's law. It's true that you can't repeal Coulomb's law, but you can screen it by Thomas Fermi screening, which we discussed in previous lectures, to make it a lot less strong over long distances. And once you've screened the Coulomb interaction, there are other mechanisms which, although they're weak, like the coupling of electrons to phonons, is sufficient to bind the electrons together. Now, there was still this question of, is the binding strength going to be large enough? We're not going to find enormous binding strength on the order, what I've written up here. We're not going to find binding strengths on the order of the Fermi energy typically, or at least for typical metals we won't. But we will find a binding potential nonetheless. Okay. Now, the actual mechanism that gives an attraction between electrons via phonons is important enough that I'm going to derive it in two different ways. The first way, so this is phonon-mediated attraction. This is what we're going to derive next. Phonon-mediated attraction. Electron-electron attraction. So I'm going to derive this in two ways. The first way is to use second quantization, which we're all familiar with, and we're going to try to derive an effective low-energy Hamiltonian, which shows an effective interaction between electrons. And then we're going to rederive it in a sort of more semi-classical way, which will maybe give a little bit more intuition. So, okay, so let's do what we usually do here. We'll write our Hamiltonian as two pieces, H0 and H1. And H0 is going to be the bare electron Hamiltonian and the bare phonon Hamiltonian. So I'll write as bare electrons and bare phonons not interacting with each other. Just the Hamiltonian for them as if they were alone. And H1 is going to be the interactions between electrons and phonons. Okay? So let's actually write out what we mean by these. So H naught, I'm going to take a really simplified form of H naught here. We'll write it as sum over K, epsilon K, C dagger K, CK. Suppressing spin indices here, which should really be there. And then for phonons, we'll take a really simple form of phonon Hamiltonian. It will be sum over Q, A dagger Q, AQ. Just counts the number of phonons or bosons at wave vector Q and gives each of them an energy h bar omega. So these are Einstein phonons, meaning all phonons have the same frequency. It's not crucial that we do this. We could have phonons with different frequencies. Just makes the calculation a little bit more complicated, but not too much more complicated, but we might as well keep it simple as possible. I've also simplified this a bit by not keeping track of the polarization of phonons. Phonons have multiple different polarizations, and I've dropped those indices, which really should be there as well. Now, one thing you'll notice about this Hamiltonian we've written is that there's no Coulomb interaction between the electrons. And I'm going to ignore that. So I'll even write that down. No Coulomb electron-electron interaction. And the reason for this is because we're assuming that the Coulomb interaction between electrons is going to be screened with Thomas Fermi screening over a fairly short length scale, so we can ignore it. Anyway, what we're interested in is actually the effect of the electron-phonon coupling. Okay, so let's actually write out the electron-phonon coupling that we're interested in studying, and there's various different ways we could write this. Let me write it in a fairly simple form, sum over Q, M sub Q. M is a matrix element. That's why we use M. Rho hat minus Q, A dagger Q, plus Hermitian conjugate. And rho hat here is the electron density operator. We've seen him before. And m is this coupling as a function of q, and just again for simplicity, we'll just take the coupling to be independent of q. So all q's have the same coupling between the electron density and the creation of a phonon. So this we can rewrite, since we know what the electron density operator is, we can rewrite this as sum of q and k. We're going to take m to be a constant, and then we'll have c dagger k minus q, c k, a dagger q plus Hermitian conjugate. And the sort of Feynman diagram way to draw this is that you have a electron coming in with wave vector k. You destroy that via this ck, and you create a electron with k minus q, and in the process you also create a phonon with wave vector q, so that overall momentum is conserved. Okay, now what we'd like to do is we'd like to figure out what the effect is of this coupling between the electrons and the phonons, with the assumption that the coupling m is weak. And the technique for doing this is, or at least one technique for doing this is known as canonical transformation, transform. And the idea here is to transform your Hamiltonian in the following way. We'll make a script h, the transformed Hamiltonian, e to the minus s h e to the s. And the idea is that once we make this transformation, this transformed Hamiltonian, we will have decoupled the electrons from the phonons, but at the price of introducing a direct electron-electron interaction, which is what we're actually interested in. So we're going to find the effect of the phonons by seeing, once we try to decouple the electrons from the phonons, what is the effective electron-electron interaction that's left over. If you're a field theorist and you like to use path integrals, what we're doing here is integrating out the phonons. So you have some path integral that includes electrons and phonons, and you do an integral that gets rid of all the phonons, and as a price you introduce a direct interaction between the electrons. And that's the interaction we're going to be interested in, which we believe is going to be attractive. Okay, so how do we deal with this? Well, order by order in S, we can write this out using the famous Campbell-Baker, I think this is Campbell-Baker-Hausdorff, isn't this? Plus 1/2 h comma s, or successive commutators. I'm not drawing this very well. Successive commutators h comma s plus dot dot dot. Okay, and the idea is then to solve this order by order in this coupling constant m, which we know is small, by choosing an s that removes the interaction of the electrons from the phonons. Okay, so how do we do that? Well, let's assume that that s is going to be small. Why is s going to be small? Well, our idea is to choose an s such that we decouple the electrons from the phonons. If m is small, then you can choose s to be 0, because if m is actually 0, then you can choose s to be 0 because they're already decoupled. There's no interaction between them. If you make m non-zero, then s has to be only a little non-zero to decouple them. So when m is small, s is also small. So let's rewrite this series, keeping track of the terms in order of their smallness. So something is small if it contains an m or if it contains an s. Okay, so the only term that has no m's or s is just h0, which comes from the regular h here. Okay, then we'll have two terms which is order 1 in small, and that will be h1 that has an m. H1 has an m, and then we'll also have h0 commuted with s. Okay, so h1 comes from this term, and h0 commuted with s comes from this term, h0 commuted with s. And then at next order, so these terms here are order 1 in small, order 1 or order small. Okay, and Then the next order term are order 2 in small, and we can have order 2 in small by looking at the H1 commuted with S term. That's when H1 is sitting here. Remember, H is made up of both H0 and H1. I'll write this out. H equals H0 plus H1. So when H1 is in here, we have an H1 commuted with S, that's order 2 in small. And then we also have plus 1/2 H0 comma S, and that's also order 2 in small. Okay, so these terms here are order small squared. Okay, now our scheme here is to try to get rid of things order by order in small. So we want to choose an S, to get rid of the order small terms, so that these things are 0. These things here are 0. Okay, and that will remove the interaction at leading order in S. It will remove H1. So to do that, we are choosing H1 plus H0 comma S equals 0, and then these terms here, these leading order 1 in small, order small to the first, terms all vanish. Okay, and then we plug the same result in here, same result into the order small squared, and you'll notice that both these terms are of the same form. And if I wrote it correctly, this is then going to be yes. So this term will exactly half cancel this term, and we'll be left with H equals just H naught, the decoupled term, plus 1/2 H1 comma S, and this is H1 comma S. H1 comma S. Okay, so H1 comma S. So this term, this H1 comma S term, is going to be the effective interaction that's left over once we so this is H int that's left over once we decouple the electrons from the phonons at first order, and what's left over here is order small cubed, which we throw away entirely. Okay, good. So how do we figure out what S is supposed to be that will solve this equation here? Well, the way to do this is to take the matrix element of this equation between two arbitrary states n and m. So we can write n h1 m equals, I guess we'll move the other one to the other side, n h naught s m, like this. And I can, well, we know h naught applied to things just gives me the energy, so this would be minus en minus em times n s m, and that means I can write the matrix elements of S, NSM, equals n h naught m divided by em minus en. So now I've defined what the operator S needs to be. Okay, and then once we know what this S thing is, we can figure out, we want to ask, what does this H interaction look like between two states in our system, maybe even states that don't have any phonons at all. So let's consider states A and B, which have no phonons, and I want to figure out what is the effective interaction between them. So A H int B. So remind me what H int is. H int is 1/2 H1 commuted with S. So this thing is going to be 1/2 A H1 commuted with S B. And I can, well, I know what S here is. We wrote it right up here. So I can then write out the interaction between A and B. I'll write it as 1/2. I can insert a complete set, so then I have A H1 C C S B minus A S C C H1 B. That's writing out the commutator. And then I'm going to use my expression here to plug in for this matrix element of S. And this gives me 1/2 sum over C A H1 C C H1 B. And then the energy denominator is EB minus EC, and the other way around it's EA minus EC. Okay, so this is with A and B have no phonons in them. This is the effective interaction between A and B. So what's actually going on here? So remember that H1 is the term that that scatters an electron and creates a phonon. So if we start in a state B over here, let's start in a state B over here with no phonons. This term, it scatters to a state C with a phonon. So this has one phonon. And then scatters back to a term A with no phonons. And in the process, there's an energy denominator associated with the energy C. So in fact, we can be a little bit more specific about this. We can even draw a diagram. So let's let B equal, so we want to have, say, 2 electrons added to the Fermi C, one at momentum K and one at momentum P. And then C will, using going all the way back up to our expression for H1, so it scatters an electron from some K to some K minus Q, and it creates a phonon in the process. So C can be of the form C dagger K minus Q, and then it has the same C dagger P and an A dagger Q on the Fermi C, and then it's going to scatter back, get rid of the phonon, back to state A, which will be C dagger K minus Q, C dagger P plus Q on the Fermi C. And let me draw a diagram of this. So it has K coming in, and it has P coming in, and they exchange a sorry, this is P coming in. Two electrons, one with wave vector K, one with wave vector P. They exchange a phonon with wave vector Q. This guy comes out with K minus Q. This one comes out with P plus Q. P plus Q. Okay? Now, the key thing to realize here is that if the phonon energy, that's EC here, well, EC is actually the energy of this whole thing here, but if the energy of the phonon is larger than the energy of the electronic excitations, then this whole expression here is going to be negative. Sorry, I have a sign wrong here. That should be a plus. So both of these terms will be negative, and that corresponds to an attractive interaction. So let me write it out in a little bit more detail. Trying to maybe make it a little smaller so you can still see what's going on here. H effective, H int, or maybe H effective, will look like 1/2 sum over P K Q, C dagger P plus Q, CP, C dagger K minus Q, CK. This is matrix element squared. And then we'll have energy denominators, 1 over EK minus E K minus Q minus H bar omega. Oh dear. I'm going to run out of space, so I'll put it here. Plus 1 over EP plus Q minus EP minus H bar omega. Okay? And again, if the energy of excitation of the electrons, that's these energies here, these energy differences, is smaller than H bar omega, then this whole thing is negative. So H int, I call it H int, int is less than 0, meaning we have an attractive interaction. In particular, if ek minus q is less than h bar omega, then we have an attractive interaction. Matter of fact, we can simplify it even more. Let's assume that it's much greater. ek minus q is much less than h bar omega. If that's true, then we can throw away these energies, epsilons, in the denominator and only keep the h bar omega, in which case what we have is h int equals minus m squared over h bar omega sum over q of rho q rho minus q, and this corresponds to a delta function interaction between electrons, and it's attractive. Okay, so the fact that we're getting a delta function interaction is a feature of the fact that we took m to be independent of q, and we took omega to be independent of q as well. That's those don't have to be true, but the fact that we're getting an attractive interaction is coming from the fact that the energy of the phonon is greater than the energy of the excitation of the electrons. So this calculation from second quantization, it seems potentially a little mysterious because it involves creating these virtual phonons. So you create a phonon, then you absorb the phonon again, and you have an effective interaction between electrons that goes via this virtual phonon. But it's something that's hard to develop intuition for. So I'm going to do sort of a more classical derivation of the same effect. So this classical derivation is going to rely on the kind of screening calculation we did when we discussed plasmons and RPA in the previous lecture. This particular calculation is going to somewhat overestimate the strength of the attraction, but it will give you some idea of how this works. So let's recall the response of a physical system. It has the charge density, we'll call it chi naught times phi. Let's write delta rho here. It's charge density. I guess when we wrote down chi naught before, we were looking at density rather than number density rather than charge density, so there'll be an extra factor of E floating around here. But chi naught here, for if we're looking at responses of electrons, chi naught at high frequency was of the form q squared average density E squared omega squared m, which we can rewrite as q squared epsilon naught omega omega plasmon for electrons squared divided by omega squared, where we derive the plasmon frequency is square root of n bar E squared over m epsilon naught. And that's for electrons, it's a very high energy scale. It's on the order of an electron volt. So it's very high frequency for this type of response. Now, what you can do is we can make a really crude model of so this model here was really just the electromagnetic. We derived this actually in 3 different ways, but one way, the simplest way, was just to think about the motion of a charged fluid. So you're making the charged fluid oscillate back and forth. It builds up a charge, and then it swings back and forth due to the buildup of the charge, and that's what a plasmon is. Now you can do the same thing with the charge of the background ions. Background ions also move as a fluid. So this is a really crude approximation where instead of thinking about our background ions as being stuck on a lattice, we're going to think of them as being a free fluid of ions. So you get the same result, but the mass of the electron becomes the mass of the nucleus, which of course is huge, and I guess the charge changes sign. That's not so important. So we'll get chi naught for the ions is going to be q squared epsilon naught omega ion plasmon for the ions squared over omega squared, where omega ion plasmon equals square root of n bar e squared over the mass of the nucleus times E naught. Well, the mass of the nucleus is huge compared to the mass of the electron. First of all, remember that a proton has a mass of 1,800 times that of an electron, and furthermore, most nuclei have a lot of protons in them. They have, even for a small atom like aluminum, you have, I don't know, what's the atomic number of aluminum? 20 something or whatever. So its atomic weight is I don't know, 30, 40, whatever nucleons, and so it's 30 or 40 times 1,800 factor in the denominator, and this ion frequency of the ion oscillation frequency, just treating it as a fluid, comes out to be on the order of the phonon Debye frequency. Both of these things are describing the characteristic frequency scale on which these nuclei respond. And this is much, much lower. So the Debye frequency is on the order of, say, 100 Kelvin for typical materials. It could be 200 Kelvin or something like that. So it's a much, much lower frequency as compared to the plasmon frequency for electrons, which is up on the 10,000 or 40,000 Kelvin scale. Okay. Now, at these very low frequencies, the electrons, this looks like it's completely static for an electron. Electrons move really, really fast. So the response of electrons is just the static response that we calculate, the static compressibility. Okay. So this is the limit we're going to be working in, where the ions are oscillating at their plasmon frequency, but the electrons are screaming as if the system is static. So it's a low frequency scale for the electrons, but a high frequency scale for the ions. Okay, so now we're going to do the same kind of thing that we did in the previous lecture. We are going to see what the interaction between the two subsystems are by writing some total potential is going to be an externally applied potential plus the induced potential. And okay, so this will be the external potential plus the Coulomb interaction times the density you build up of the electrons plus the density you build up of the ions. Okay. Now, exactly as we did before, we'll then write the density of electrons as the electrons' response. Okay, and now I put the. All right. Well, let me put this upstairs and 0 downstairs. 0 means we're treating non-interacting electrons. We're not worrying about their interaction with each other. This is exactly what we did in RPA. The electrons respond as if they were non-interacting, but they are responding to the total potential, and part of the total potential is whatever potential the other electrons create. And then the ion density is going to be the ion response times the total potential. And I guess, yeah, okay, I wrote it correctly here. Chi ion superscript 0. Okay, so then we just want to take this equation and solve it for phi total in terms of phi external. That's easy enough. So phi total equals phi external divided by 1 minus v twiddle of q chi naught electrons plus chi naught ions, and chi naught of ions is actually a function of Q and omega. Chi naught electron, we just took it to be a number, just the compressibility because it's static. And similarly, the effective interaction between any two charged objects is going to be screened the same way. So this will be V of Q divided by, so for the electron-electron interaction is V twiddle of Q between two electrons, and it gets screened exactly the same way. V twiddle of Q, chi naught E plus chi naught ion, the function of Q and omega. And we will now plug in the expressions we just derived for both of these quantities, and we'll get that this is V twiddle of Q, and is screened by 1 plus k Thomas Fermi squared over Q squared. That comes from this term only, and then the ion term is minus omega plasmon ion squared divided by omega squared. Okay, so there are a couple things to notice about this expression for the effective interaction between electrons. First of all, if you throw away the plasmons altogether, just drop this last term, you just get Thomas Fermi screening of interaction between electrons. So at wave vectors that are longer than the Thomas Fermi wave screening length, the interaction gets damped. Okay, this will give you the Yukawa form that we derived in a previous lecture of interaction between charges in your system if you drop this term with the plasmons. A second thing to notice is that if you go to frequencies which are much, much higher than the Debye frequency of the phonons, then this term with the ions will vanish altogether. So maybe I'll write that down. Maybe I'll write all these points down. One, with no phonons, we get Thomas phonons. We get Thomas Fermi. And 2, at omega much greater than omega Debye, then we have the phonons don't matter. Phonons don't matter. Because this whole term will drop to 0 as well. 3, at if you take omega equals 0, then you get perfect screening. Why is this? Okay, let's look at this for a second. If we take omega equals 0, then this term down here in the denominator blows up, and the effective interaction drops completely to 0. So this is small omega going to 0. The denominator blows up, the entire interaction goes to 0. And the reason for this is because if you go to 0 frequency, then my ion fluid can come in and perfectly screen any charges I put in the system. So if I put an electron at some position in the system, the ion fluid can come in and completely neutralize it, so that the interaction is completely destroyed. But the last point, 4, is that for small omega, you'll notice that the interaction is attractive here, right? Notice that this term will dominate the denominator, and it comes with a minus sign. Okay, so the picture that we should have in our head is that an electron, a charge, polarizes lattice, and then moves away from that region. The lattice responds, but very slowly. Once the lattice responds, there becomes a region which is now net positive. I mean, it started to move because it was trying to screen the presence of an electron, but by the time the lattice has moved there to build up a positive charge, the electron is gone. But another electron can be attracted to that region. So an electron polarizes the lattice, leaves region with plus charge behind. Another electron attracted to that region. Okay, Now, this screening picture that we have of the attractive interaction between electrons via a perfect phonon fluid is actually, it was shown somewhat later, that it predicts an attraction which is actually much too strong, which is a little surprising, but it gives you an idea of how the mechanism works. A cartoon picture that you often hear talked about is, I'll give the words because you hear people say it all the time, is the idea of a matress model. And I don't think this is actually a good model, but you imagine two objects sitting on a mattress. So like this, it's okay here. Imagine putting two bowling balls or two people on a mattress like this, like that. So this is two objects which polarize the background. They distort the background. And then these two objects will actually be attracted towards each other because of the distortion of the background. I don't think this is quite a good model because this is not dynamical, and it's very essential that the model be dynamical, but people still talk about this matress model as distorting a background and inducing an interaction because of it. Okay, maybe it's good to stop this lecture here, and we'll start the next lecture with the issue of bound states and the Cooper problem. Hi, welcome back. I still have my coffee. So this lecture we're going to discuss bound states and what's known as the Cooper problem, which describes binding of electrons. In the previous lecture, we explained how phonons can, in principle, create an attraction between electrons. In the first calculation we did, we saw that the attraction was weak. It's order of the coupling between electrons and phonons squared. But at least there's an attraction that can be generated. And the first question we want to ask, this is an important question, is if we have an attractive interaction, if we have an attractive potential, attractive interaction, maybe we'll, instead of thinking about two electrons, let's think about just one electron in a well. So, by going from, if I'm talking about two particles, by going to relative coordinates, I can think about it as a single particle in a well instead of two particles attracting each other. So if we have an attractive potential in d dimensions, and potential is weak, is there a bound state? Okay, simple question about quantum mechanics. If you haven't seen this before, the answer is to this, we'll derive it, is in d less than 2, the answer is always yes. No matter how weak the potential is, you can find a bound state for any attractive potential in d less than 2. In d greater than 2, it's no, or at least not for very weak interactions. For strong enough interaction, of course, you can have a bound state, like a hydrogen atom. But for an arbitrarily weak interaction, you don't generally get a bound state. D equals 2 is tricky, but the answer is usually yes. So we're not going to treat the d equals 2 case because that one's complicated, but we'll do all other dimensions. So let's prove this in general. So we'll take a case of general dimensions, although I'll draw everything in one dimension because I can't draw higher dimensions. So we're going to imagine a general potential, which with the constraint that it goes to 0, which is 0 outside of some radius, outside of radius r. Okay, and the magnitude of the potential, is less than v0 inside r, inside the radius r, with v0 small. So we can use this proof more or less works for any shape potential, but you'll get the general idea of how it works if we just take a box potential, particle in a box potential is good enough. Not infinitely hard walls, so it'll be finite hard walls. So let's draw the picture here in one dimension. So here's like that. So this is energy on this axis. This is x on this axis. Here's it could be radius, I guess. Here's position 0, and then I'll give a box potential of let me draw it like this. So it has exactly 0 energy outside of some radius, exactly 0 energy outside of some radius, and then within that radius it has a depth. So this is radius r here, and it has a depth v naught. Okay. So that's the example potential we're going to use. Now, if we want to ask if there is a bound state, so a bound state means that energy is less than 0. And if you imagine a state with energy down here less than 0, that just by using WKB approximation, the wave function must decay exponentially as when you're outside of this radius. So you're sort of tunneling. Once you're below the energy of the potential here, once the energy is below the energy of the potential, the wave function must decay exponentially as you penetrate into this what is acting like a wall, a confinement potential here, and so the wave function must decay like this. So maybe let's even draw what the wave function kind of looks like. It'll look like something like this, and it's going to decay exponentially. Okay, good. So outside of the potential, it will look like this. Inside of the potential, it will have some peak, maybe kind of like this, like I've drawn here. And we must have I guess we should say one more thing, that if energy is very small, so it's very weakly bound, then this length scale is long, very long. So this length scale of binding can get very, very long if the energy is bound just below 0. So we're thinking about very weakly bound bound states. So we also must have normalization of the wave function. So integral psi squared d of r has to equal 1, and that implies that the magnitude of the wave function, if the length scale of the wave function is some number, here we call it L being the length scale of the wave function. Maybe I'll write that here. The length scale of the wave function is L here, longer than R. So if the length scale of the wave function is L, then the magnitude of the wave function has to be 1 over L to the d over 2, such that when you square it and you integrate it in d dimensions, you can get 1. Okay. All right. So now let's just do an order of magnitude estimate of the terms in the Schrodinger equation. So the terms in the Schrodinger equation, if L is long, there's a potential term and there's a kinetic term. So the potential term is, so it has an energy minus V naught, and it's minus V naught over a region, ddr of psi squared, over a region of size r. Only goes up to a ball of size r to the d. So this will be roughly V naught r over L to the d power. and the the 1 over L comes from the size of the wave function. So we're just plugging in this expression for psi squared, and we're integrating out to a radius r. Maybe just call it ball of r. Okay, so that gives us an estimate of the potential energy. On the other hand, the kinetic energy is going to be h bar squared over 2m L squared, because L, if L is the decay length, that's the more or less 1 over L is the wave vector, so that the kinetic energy plus the potential energy is going to be h bar squared over 2m L squared minus v naught r over L to the d. And it's easy to see that for d less than 2, for large enough L, this is negative. And that means a bound state. Okay? Because this term will dominate at large enough L. For d greater than 2, then for very large L, it's positive, so you get no bound state. So no bound state. Now for strong enough potential, you can still make a bound state, but for very weak potential, what is that? Hold on. Okay, someone didn't know how to turn off their cell phone ringer. So as I was saying, the point here is that for d greater than 2, you cannot get a bound state just by going to large enough L. And generically, that means that for weak V, for weak attractive potential, you do not get a bound state in dimensions greater than 2. Of course, for a strong enough potential, like for example a hydrogen atom, you can get a bound state in any dimension, but not for arbitrarily weak potential. So let me actually write down the conclusion and we're interested in 3 dimensions in particular. In d equals 3, no bound state for very weak potentials, for weak potential. And that actually sounds pretty bad for our attempt to try to form a bound state from the weak attractive interaction which is induced by phonons, from the weak attractive interaction between electrons which is induced by their interaction with phonons. It seems like it's going to be a pretty tough problem to try to figure out how are we going to bind electrons together. So the whole story of superconductivity was broken open by Leon Cooper in what is now called the Cooper problem. Leon Cooper, 1956, where he showed that the issue of whether you form a bound state or not is completely different if you're thinking about 2 single electrons just hanging out by themselves, or if you're thinking about 2 electrons and a Fermi sea. What he concluded was that 2 electrons on top of a Fermi sea, do form a bound state, for arbitrarily weak attractive interactions. And the we'll go through the calculation because it's important, but the key piece of information is that if you're making a wave function for fermions above a Fermi sea, all momenta that you use must be greater than kf. So your wave function can only include momenta greater than kf because all of the momenta less than kf are already filled with other electrons. Okay. So how do we show this to be true? The way to do this is we write a trial wave function for 2 electrons. So we'll write it like this. psi of R1 sigma 1, R2 sigma 2, and we'll write it as spin 1 up, spin down 2, minus down 1 up 2. So this is a spin singlet. And then a spatial part, so 1 over the volume, sum over k greater than kf, e to the I k dot R1 minus R2 and g sub k. Okay, so this part here is some sort of g of R1 minus R2, and I've just written it in Fourier notation. So a couple things about this wave function. First of all, it has to be antisymmetric because we're talking about electrons. Then a singlet is already antisymmetric. So that means the spatial part should be symmetric. Okay. In order to get the spatial part to be symmetric, we should have g of k equal g of minus k, and if we want it to be rotationally invariant as well, we might even go further and say that g should be a function of absolute k only. The second thing I should comment is that this argument, all of BCS theory, does not rely on pairing electrons together in singlets. It turns out that the vast majority of superconductors known do have electrons that pair together in singlets rather than in triplets. So it makes sense to do the calculation for singlets, but you can also do the calculation for triplets. It's maybe a tiny bit more complicated, but not too much more complicated. Another thing to realize here is that on the right-hand side, this wave function is a function of R1 minus R2, but is not a function of the center of mass of our center of mass is R1 plus R2 over 2. That doesn't enter at all. And what that's telling us is that we're taking this pair that we've written and put it in a plane wave at k equals 0. So we put the center of mass momentum to be 0. There's maybe a slicker way to write this trial wave function. To do it in second quantized notation, we'll write psi is 1 over the volume, sum over k greater than kf, g sub k, c dagger, k up, c dagger minus k down on the Fermi c. And the fermionic anti-commutations guarantee that this combination is creating a singlet. And it also guarantees that it has the right Pauli antisymmetry. Okay, so then with this trial wave function, we're going to assume some attractive interaction, which might be weak attraction, u of R1 minus R2, which may be weak if we want, and we would like to solve the Schrodinger equation. Solve Schrodinger, which we'll write it in the following way: the kinetic energy plus the potential energy minus the eigenenergy on psi equals 0. Okay, so let's try to plug in our wave function into this expression, and to do that, let me just actually copy our wave function here. Dun, dun, dun. Amazing, I can do this. I say this every time, it's so amazing. Modern technology, never get tired of it. Okay, paste. Okay, there it is. So that's the wave function we'd like to plug in. So I'll write plugging this in, I'll write what we get as follows. So it will be a sum over k, g of k, we'll have the e to the I k dot R1 minus R2, like this. The kinetic energy term, well, each time we create an electron with a plane wave momentum k, we get some energy E of k, and in fact there's 2 electrons with the same energy. We've created 2 of them with the same energy, one with k and one with minus k. Those have the same energy. So the kinetic energy term is 2 E of k here. The potential energy term is going to have U of R1 minus R2, and then minus E equals 0. Okay, this is just from plugging in the wave function into the Schrodinger equation. Okay, now to solve this, we Fourier transform, integrate with d dimensions of r1 minus r2, or relative coordinate is the thing we're Fourier transforming. So q r1 minus r2, and at the same time we're going to define the Fourier transform of u of r, the potential, 1 over volume, sum over q, u twiddle of q, e to the I q dot r. Okay, so making that Fourier transform, we get 2 energy of q minus e times g of q, plus the Fourier transform of this term here is going to pick up, well, we're going to get sum 1 over volume, sum over k greater than kf, u twiddle of q minus k, gk, all equals 0. So how did that happen? Well, okay, there was a k dot r here, but there's also a q dot r here, so we end up getting q minus k gk over here. If I did that carefully, yeah, there's a minus there, making this minus. Okay, good. And this equation is what we're going to work with, but it's still rather difficult analytically. So what we should do is think about simplifying this, even if it's even if the simplification looks like it might be an oversimplification. So remember that when we considered the physical phonon attraction for phonons, the actual thing we're interested in, we found attraction for energies which are less than the phonon frequency. So attraction for energy less than the phonon frequency. So h to bi. So let's just take a model, this Cooper's model of a interaction potential u, which is extremely crude and actually looks even a little bit unphysical. We'll write it this way. Instead of writing it as a function of q minus k, I'll write it as a function of q and k, and I'll write it as minus u naught if both energy of k and energy of q are both within h bar omega to bi, h bar omega to bi of the Fermi surface, and is 0 otherwise. So if both k and q are close to the Fermi surface, closer than this maybe, so this is really I should have written here minus EF less than h bar omega to bi. So if both of these things are close to the Fermi surface, you get minus u, and if not, you get 0. Now it's a little bit of a weird interaction because it's not really it should be a function of k minus q, not k and q separately. So it looks kind of strange. It sort of has some of the properties that we want of an interaction, but the reason we use this is because it's analytically tractable, and that's a huge advantage. So let's plug in this form into this equation. We do that, we get 2 epsilon q minus e times g sub q minus, I guess, this u naught over volume, sum over k greater than kf, g sub k equals 0, subject to the statement that e sub k must be less than ef plus h bar omega to bi. Okay, so good, and this also must have e sub q has to be close to the Fermi surface also. So Q close to Fermi surface also. Okay, for this equation to have been derived. All right, so what do I do with this? So here I'm going to switch from a sum over k to an integral over energy. So I'll write it as U naught density of states of the Fermi surface integral d energy from the Fermi energy to the Fermi energy plus h bar omega dubai, and the thing I'm going to be integrating is g sub k, but let's k is going to be a function of e, and we're going to assume that g is a function of absolute k. I'll write it as g of k, and k is a function of e, g of k of e, like this, g of e, or maybe we can just write it as g of e if we like. So all I did here was to replace this sum over k's with an integral over energy times the density of states. So this, just to be careful, this d here is the density of states per unit volume. And we're going to assume that that's close to a constant near the Fermi energy. So it's just density of states in EF. Okay? So, good. So we can then solve this equation for g of q by moving this factor under this factor, move this whole thing to the other side, and then divide through by this factor. So I get g of k of energy here is then u naught d of EF integral EF plus h bar omega dubai dE, g of k of E. Maybe I'll write that as E prime because we have an E sitting over here. Yeah, so I want to write this. It's, this one probably should have been Q, g of Q of E. Q of E. That's from this Q here. G of Q of E, and then the thing that comes over here. I move this all over to this side. E of Q minus E. I can then drop this Q. So this is. Sorry, I'm going to make an eraser. No, I shouldn't make an eraser transform. Let me draw exactly the same equation here. Copy, paste it again, paste. So G is now going to be a function of E only. G is a function of E, and then G over here is also a function of E. Like this. Good. Let us define this numerator to be a number called C. So C is U naught density of EF integral of EF to EF plus h bar omega dubai dE prime G of E prime. And so that means that this equation can be written as G of E is, I guess, C over 2 E. Here, this is no longer a function of Q, it's just E. Yep. So this is now 2E. 2 epsilon minus eigenvalue E. And then the way to solve this is to realize that I can calculate C again by plugging this G in here. So we get C equals U naught d EF integral EF to EF plus h bar omega dubai the epsilon prime C over 2 E minus E. We can cancel C on both sides, and then maybe move the U naught over to the other side. So we get 1 over U naught d of EF is integral EF d E to EF plus h bar omega dubai 1 over 2E. God, that should be a prime up there. Minus E, like this. We can do that integral to get 1/2 log of 2 EF minus h bar omega dubai minus E divided by 2 EF minus E, which basically gets me to the, oops, well, I come back, gets me to the solution. Exponentiating both sides, we then have e to the, let's move the 2 over from this side to this side, so we have e to the 2 over u naught density of states to the Fermi surface equals the exponential of this log is 1 plus 2 h bar omega debye over 2 ef minus e. Good. So what is this? This is our final equation. It's important. For small u, small attractive interaction, for small u naught, what do we have? Small u naught, the left-hand side over here is huge. The only way the left-hand side can be huge is if the right-hand side here has 2ef minus e. It is small but positive. So this happens if 2ef minus e is small but positive. And that means e is less than 2ef, which means we have a bound state. Why? Well, the energy of the electrons that we put in, the momenta of the electrons that we put in are above EF. So we put in electrons above EF, but when they interacted with each other, they ended up having an energy below EF, which means we have binding, that the net energy of interaction is below 0, and so we have a bound state. Now we can go a little bit further. For small u naught, we know that both sides of this equation are large, and so we can drop the 1 and rewrite this equation as e to the 2 over u naught density of states at EF equals 2 h bar omega debye over 2 EF minus E, or another way of saying it is the binding energy 2 EF minus E is 2 h bar omega debye e to the minus 2 divided by u naught density of states at the Fermi surface. So this is the strength of the binding, and it is exponentially small in 1 over the attraction strength u naught, and it's quite important to realize that this is non-perturbative. What do I mean by that? If you think about the function e to the minus 1 over x, minus 1 over x, and you try Taylor expanding that around x equals 0, it has no radius of convergence. Has no radius of convergence. At x equals 0. So no order Taylor series will ever represent e to the minus 1 over x if you're expanding it around x equals 0. And that's exactly what we have here. We have a binding energy, and this is not supposed to be divided by binding. Maybe I'll just write it this way. This is the binding. So that we have a binding energy here, which goes as e to the minus something over u naught, and u naught is small, which means that no order in perturbation theory will predict this binding. Which is one of the reasons why it took so long to figure out BCS theory. It's also important to realize that the Fermi C is crucial. Fermi C is crucial. In particular, the density of states at EF must be not equal to 0 here. Otherwise, if the density of states here was 0, you would get no binding. So it's really coming from the finite density of states at the Fermi C, which assures that you can have binding energy even if it's exponentially small. And this is the arbitrarily weak U naught will still give you binding, even though it's exponentially weak binding, but it is binding nonetheless. So this actually was the hint that launched BCS theory. And the reason that, you can sort of understand what's going to happen here. So you start with a Fermi C. Let's draw a Fermi C. There we go. We start with a Fermi C and it's filled. And then some of the electrons in the Fermi C realize that one's right at the Fermi surface, realize that they can come out of the Fermi surface. I guess it's they form a pair, one with plus k and one with minus k, and they form some pair here that they pair together. Oops, these guys pair together with each other. This guy pairs with this guy, and they manage to lower their energy. If they were right at the Fermi surface, their energy was 2EF, but by coming above the Fermi C, pairing together via this phonon interaction, they lowered their energy. So now they have a lower energy, and then another pair can come out of the Fermi surface and form a pair like this, and then these two lower their energy, and you realize that what's going to happen is you're going to have a complete instability of the Fermi surface, stability of Fermi surface, and this is what signals the presence of this pairing instability towards superconductivity. So in the next lecture, we'll try to understand what happens when you have all of the electrons trying to pair with each other. Okay. Till next time.